going to investigate rational functions. We're going to talk about the properties of rational functions and then conclude with learning how to graph a rational function. A rational function is a function that's written as a fraction. So r of x is equal to the ratio of two polynomials p of x over q of x, where q of x does not equal 0. And that's, again, from the restrictions of a rational function, which we've talked about in previous lessons. Now, the domain of a rational function is the set of all real numbers for which the function is defined. And to recall, that means we're just going to exclude any values that make the denominator equal to 0. So let's review how to find the domain of a rational function. We have 3x cubed divided by 6 minus 2x. To find our restrictions, we're going to set our denominator equal to 0 and solve. So we subtract 6 from both sides. Negative 2x equals negative 6. Divide both sides by negative 2. We get x cannot equal positive 3. When we just leave it like this is called stating restrictions. We can also write the domain in interval notation. And if I use a graph to help me out with that, my only restriction is 3, so I can be any value to the left or any value to the right. My first shaded region is represented by the interval negative infinity to 3, not including 3. And my second shaded region is from 3 to positive infinity. Let's look at another one. Negative 4x divided by x squared plus 2x minus 8. Again, to find our restrictions, we set the denominator equal to 0. X squared plus 2x minus 8 equals 0. And this is a quadratic function, so we'll factor it to find the zeros. We need factors of negative 8 that sum to positive 2. So this is positive 4 and negative 2. And from here we can see that x cannot equal negative 4 and positive 2. And if the question allows us to just state the restrictions, this is fine. But if the question wants the domain in interval notation, again, a graph might help us. Here's negative 4, here's 2, and these are the only restrictions. So I can be anything to the left of negative 4, anything to the right of positive 2, but the section that's most often forgotten is this section between negative 4 and 2. So now we'll have a different interval for each of my shaded regions. Negative infinity to negative 4, union negative 4 to 2, union 2 to positive infinity. F of x equals 3 divided by x squared plus 2. Setting my denominator equal to 0, I have x squared equals negative 2. And now I start thinking about taking the square root of both sides, maybe adding plus or minus, but the issue here is that I've got a negative underneath the radical, and I cannot take the square root of a negative number and have it be a real solution. So there are no restrictions for this rational function. And we can think about this just in terms of number sense. X squared plus 2. Well, if we think of our possible inputs, if x is a positive number, x squared is positive, and add 2, that's more positive. If x is negative, a negative value squared is still positive, and then you add 2, it's more positive. The only value I haven't considered is 0. 0 squared is 0, but when you add 2, it's still positive. So this denominator of x squared plus 2 is always going to be positive. It's never going to equal 0. So if there are no restrictions, then our domain is from negative infinity to positive infinity. So just to recap, talking about domain again, we saw problems that had restrictions. Then we also saw a rational function that had no restrictions. The domain was still all real numbers. So it is possible that we have a rational function with a domain of all real numbers. Next, we're going to talk about asymptotes. When we were looking at our library of functions, we looked at the reciprocal function, which was the parent function for rationals. And we did introduce asymptotes. We talked about it being that vertical or horizontal line that kind of acts like a force field where our graph doesn't cross or touch it. Now we're going to get into a bit more specific definition of these asymptotes. So a vertical asymptote are the zeros of your denominator when your function is in lowest terms, which means that your function must be simplified before you find your vertical asymptote. Since we are still finding zeros of the denominator, we're going to investigate the relationship between the vertical asymptotes and your restrictions that we found in the previous examples. Find the vertical asymptotes of the function f of x equals 3x divided by x minus 2. Well, if I look at this function, the first thing I want to verify or find is the restrictions. We know that x cannot equal 2 by looking at the zeros of my denominator. Then we need to consider simplifying this function. Is there anything that I can do to my numerator or my denominator to factor and then cancel anything out? By looking at it, no, there's no way. This is already simplified. So now that we know that it's already in lowest terms, now we can identify the vertical asymptotes. Your vertical asymptotes are an equation of a vertical line. Remember how we write the equation of a vertical line? It's x equals a number. So my vertical asymptote is going to be at x equals positive 2. So there's just a friendly reminder that we're using the equation of a vertical line, which is x equals a constant. G of x equals x squared minus 64 divided by x squared minus 5x minus 24. First, we think about trying to find our restrictions, the domain for this, and that's by factoring the denominator. So if I look at my function, I know that the denominator can factor x and x, factors of negative 24 that sum to negative 5. It's going to be negative 8 and positive 3. So I can see right away that x cannot equal positive 8 and negative 3. But this is not finding my asymptotes. In order to find my asymptotes, I need to simplify that rational function. In order to simplify, I also need to go ahead and factor the numerator. X squared minus 64 is a difference of two squares. It factors to x plus 8, x minus 8. So now we can see that we've got a factor of x minus 8 that simplifies out. So my function g of x simplifies to x plus 8 divided by x plus 3. Now that my function is simplified, the zeros of my denominator are where my vertical asymptotes are. So my vertical asymptote is at x equals negative 3. Now let's talk about this value of 8 because it's still not in my domain. This function g of x, even though we simplified it down here, has the same restrictions. So x can still not equal 8. X equals 8, becomes a whole. Remember, we talked about wholes when we were learning about piecewise functions, and we were looking at the endpoints of the restricted domains. If the endpoint wasn't included, we would use a whole in that graph. The same thing here. We're going to end up having a whole in the graph where x equals 8. H of x equals 4 divided by x to the 4th plus 4. Now, I can't factor my numerator, so I know nothing's going to cancel out. This is already in simplest form. So the restrictions that we get for the domain are going to end up being the same thing as my vertical asymptotes. But if we pay close attention, x to the 4th plus 4, using that number sense again, x to the 4th is always going to be greater than or equal to 0 because of that even exponent. If I plug in a positive number or a negative number for x and you raise it to the 4th power, that's always going to result in a positive number, and adding 4 is even more positive. So there is no restrictions for this function, which means that there are no vertical asymptotes. So we've seen some examples now, and we're seeing that the restrictions sometimes end up being vertical asymptotes, but not all restrictions end up being vertical asymptotes like we saw in the previous example. Some things to remember about vertical asymptotes. The most important thing is that it's the zeros of your denominator when your function is in lowest terms. So we always have to simplify first. We always want to make sure that we write our vertical asymptotes as an equation of a vertical line. And we also want to comment that they are related to our restrictions, but not necessarily the same. Now, the next type of asymptote we're going to talk about is a horizontal or an oblique asymptote. An oblique asymptote is actually a slant asymptote. And a horizontal asymptote, just a horizontal line. Again, oblique is that slanted asymptote. Both of these are grouped together because we determine your horizontal or your oblique asymptotes the same way, looking at the degree of your numerator and the degree of your denominator. So for the case of, or for the sake of our notes, we're going to call the degree of our numerator m and the degree of the denominator n. There are three possible cases. M is less than n, m is equal to n, or m is greater than n. And we're going to look at all three of these cases individually and see how that determines what our asymptotes will be. In the first case, m is less than n. We call this a bottom-heavy function. That's just saying that the degree in the denominator is larger than the degree in your numerator. When the degree in the denominator is larger, your horizontal asymptote is at y equals 0. It's always the x-axis if it's bottom heavy. Just like we saw with our vertical asymptotes, we used an equation x equals. Since it's a horizontal line now, we're using y equals for our horizontal asymptotes. The second case are where the degrees are equal. If the degrees are equal, your horizontal asymptote is at y equals the ratio of lead coefficients. So we're going to end up with a fraction for our value, and it's going to be a fraction formed by taking the lead coefficient of the numerator over the lead coefficient of your denominator. So just to show you real quick, if I've got f of x equals 3x squared plus 4 divided by, let's call it x squared minus 2. Since I can see that the degrees in the top and the bottom are the same, my horizontal asymptote is at y equals 3 over 1, or just 3. And we'll see some more examples of finding our horizontal asymptotes in just a minute. Now, if the function is top-heavy, in other words, the degree in your numerator is greater than the degree in your denominator, we do not have a horizontal asymptote. But there is a possible oblique asymptote. Now I want to indicate and highlight that it's only a possible oblique asymptote. We will only have an oblique asymptote if the degree in the numerator is exactly 1 more than the degree of your denominator. Okay, so that's what we're going to use as our indicator for an oblique. The degree in the top is exactly 1 more than the degree in the denominator. So let's say an x cubed divided by an x squared, or an x squared divided by an x. It won't happen if you've got x to the 5th divided by x cubed, because there's a difference of 2 between those 2 degrees. Now, if I know that there is an oblique asymptote, the way that we're going to find it is by using polynomial division. So we have either an option of long division or synthetic division for polynomial division. Long division always works. Synthetic division we can only use, remember, if we're dividing by x minus c. So that I call it my naked x. There's no coefficient on x, there's no exponent on x. Once we perform the polynomial division, we're looking for the quotient without the remainder, and that's what ends up being our oblique asymptote. Again, once we divide those 2 polynomials, we're going to divide the numerator by the denominator. The result is our quotient, and then we usually have a remainder. The quotient without the remainder ends up being the oblique asymptote. And we'll see an example of that in just a minute. When we're looking to find our horizontal or oblique asymptotes, the first thing you want to do is determine which of these cases does your rational function fall into. So finding horizontal or oblique asymptotes, This first example, I think, is different than what you have in your notes, so just make the change real quick. The function we're going to be using is g of x equals x squared divided by 3x cubed. I think it might say squared in your notes, so double check that. It should be 3x cubed minus 2x plus 1. Now, to determine horizontal and or oblique, let's look at our degrees. The degree in your numerator is 2. The degree in the denominator is 3, so this is bottom heavy. And anytime a function is bottom heavy, you know that your horizontal asymptote is at y equals 0. Our next function, g of x equals 2x to the fourth divided by 3x cubed minus 4x to the fourth plus 2. Now, if I just look at this real quickly and don't pay any attention to the denominator, I see x to the fourth, x cubed, x to the fourth over x cubed, and I'm thinking this is top heavy. But if I look a little bit more closely, I actually see that my denominator is not in standard form. My exponents are not in decreasing order. So the first thing I want to do is just rewrite this function so that the denominator, that polynomial that's in the bottom, is in standard form, which is negative 4x to the fourth plus 3x cubed plus 2. And now I can see that the degrees are actually equal. When the degrees are equal, we have a horizontal asymptote at y equals the ratio of our lead coefficients. So the lead coefficient in the top was 2. The lead coefficient in the bottom was negative 4. So this is 2 over negative 4, which simplifies to negative 1/2. G of x equals x squared minus 2 divided by x minus 3. Now we have that example of being top heavy. And because it is top heavy by exactly 1, the degree in my numerator is exactly 1 more than the degree in the denominator, then that means that I will have an oblique asymptote. Oops. Sorry, guys. All right, there we go. So how do we find our oblique asymptote? We're going to use polynomial division. I'm looking at my denominator, and since my denominator is x minus 3, that means I can use synthetic division. Synthetic division, the number that goes in there is the opposite of that, so 3. And then we start listing out our coefficients of the numerator. My coefficients are 1 in front of the x squared, and we have to remember to use a 0. That's our placeholder for the linear term. And then negative 2. We bring down the 1. 1 times 3 is 3. We add vertically. 0 plus 3 is 3. 3 times 3 is 9. Plus negative 2 is 7. This is our remainder, which we don't care about when we're finding oblique asymptotes. These are the coefficients of our quotient. So our quotient is actually y equals 1x plus 3, and this happens to be our oblique asymptote. Okay, so let's just recap that problem real quick. Again, our function was top heavy, which doesn't necessarily indicate that we have an oblique asymptote. We have to check that the degree in your numerator is exactly 1 more than the degree in your denominator. If it's not, let's say it was x cubed minus 2 over x minus 3, then we don't have any horizontal asymptotes, no oblique asymptotes. Because the degree in my numerator was exactly 1 more than the degree in the denominator, then I knew that I had an oblique asymptote. To find my oblique asymptote, I divided. I took my numerator, divided it by the denominator, and I did that using synthetic division. So I set up my synthetic division. What I had to remember here when I was writing my coefficients for the numerator, I had to use a placeholder for my x term because the numerator is x squared plus 0x minus 2. The placeholder is absolutely mandatory for synthetic division, so don't forget that. And then we went through our synthetic division like normal, and we found 1, 3, 7 as our answers, those values at the bottom. The 7 is our remainder, which we don't care about for an oblique asymptote. The only thing we care about is the quotient, which ends up being 1x plus 3. Y equals x plus 3 is our oblique asymptote. So now we're going to put these concepts together to graph a rational function. So we're going to first find the domain, then we're going to find the asymptotes, the horizontal, vertical, and or oblique, finding your x and your y intercepts, and then plotting at least 2 points on every branch. Now, when we find our x and y intercepts, we're finding some of the points. They're just usually pretty nice points to graph. I actually don't care if you have exactly your x and y intercepts. What does matter is this right here, that you have to have 2 points on every single branch. When I say a branch, I'm referring to the different pieces of the graph. If you remember that reciprocal function in our library of function, we had 2 pieces. Those are both branches. So let's look at one. Let's try finding or graphing x squared over x squared minus 4. The first thing we need to do is find the domain. That's going to find all of our restrictions. So I need to factor the denominator. This is a difference of 2 squares, x plus 2, x minus 2. So I can see now that my domain is that x cannot equal plus or minus 2. Then I can start finding my restrictions, my asymptotes. I always want to simplify before I find my vertical asymptotes, and it will also work for finding horizontal asymptotes. The only thing we cannot do before the only thing we must do before simplifying is find our domain, state our restrictions. Since I can't simplify this function any further, I can go ahead and start stating my vertical asymptotes. My vertical asymptotes are at x equals 2 and x equals negative 2. Since my degrees are equal, I'm going to have a horizontal asymptote at the ratio of our lead coefficients. So my lead coefficient in the numerator is 1. The lead coefficient in the denominator is 1. So it's 1 over 1 or just 1. Our x-intercept, and I'm actually going to scoot that over just a little bit so we have a little bit more space. To find our x-intercepts, we're going to plug in 0 for y. So 0 equals x squared over x squared minus 4. It doesn't really matter if you use the factored version or not. When I solve this, I'm going to start by multiplying both sides by x squared minus 4. Those are going to cancel out on the right. 0 times x squared minus 4 is still 0, equals x squared. And if I take the square root of both sides, even adding plus or minus, we're going to find that our x-intercept is at 0. So we have an ordered pair at 0, 0. Since my x-intercept is at the origin, that also tells me that that's my y-intercept also. Now let's look back at what we just did to find our x-intercepts. We set the function equal to 0. Now, regardless of what my numerator or my denominator are, the first thing I'm going to try to do is clear that denominator, multiplying both sides by whatever that is. Those are going to cancel out on the right, and what's going to happen on the left every single time? You're going to be taking 0 and multiplying it by the denominator, which is always going to result in 0. So, in summary, finding our x-intercepts is just finding where your numerator equals 0. All right, so let's put together what we have here. I'm going to start by graphing my asymptotes. I have vertical asymptotes at -2 and +2. And a horizontal asymptote at +1. Our x and y intercepts, are at the origin. And now I need to find some other points so that I can graph my branches. If you look, my vertical asymptotes divide my graph into 3 sections. One right here, one in the middle, and then one on the right. So I'm going to end up with 3 separate branches for this graph. I need to make sure that I plot 2 points on every single branch. So now we can just start making a table of values, plugging in values for x, finding the y values, and plotting those points. So I'm going to do that up here. For my left branch, let's plug in -3 and -4. When we plug in x equals -3, we get 1.8 approximately. For this, guys, if you end up with a rational answer, make sure you just keep that as a simplified fraction. Don't use a decimal. But for the purposes of drawing this by hand, we need to approximate that decimal. When we plug in -4, we should get +4/3. And all I'm doing, making sure that you guys are aware of how I'm finding these y values, I'm taking these x values and plugging them into our function. So at -3, we're at 1.8, which is about there. At -4, we're at 4/3, which is about 1.3. So a little bit closer to that horizontal asymptote. And our horizontal asymptote and our vertical asymptote are going to kind of shape that one branch and go through those 2 points. So that's our left branch. Now continuing, we've got a point at 0, 0. We need at least one other point on this branch. So let's plug in x equals 1. When we plug in x equals 1, we get -1/3, which is about there. And we also want to plot another point. Something that we hadn't discussed previously is that our function can actually cross a horizontal asymptote. Our horizontal asymptotes are describing just the end behavior of our function. So when we were talking about polynomials, we talked about the tails of your graph where they went. With polynomials, they went both up, both down, or they went like this. For a rational function, your horizontal asymptote is what's describing where your tails are approaching. So since it's only talking about the tails, it's not really telling us what's happening in the middle. So it is possible that your function crosses the horizontal asymptote. So to see if this is going to cross our horizontal asymptote, let's see what happens when we plug in x equals -1. When we plug in x equals -1, we get -1/3. So that's this point right here. And now I can see that this middle branch is actually going to have kind of a parabolic shape. Many students get very concerned when I start telling them that your graph can cross your horizontal asymptote. It typically doesn't end up being a big deal though, because you'll find that right away. Usually it's your x-intercept or your y-intercept where the graph crosses the horizontal asymptote, but not always. Now we need to graph our right branch. So again, I'm going to pick 2 values. Let's plug in 3 and 4. Now based on what we saw in this middle section, when we plugged in +1, we got -1/3, and -1, we got -1/3. What do you think is going to happen when you plug in +3 when -3 was 1.8? Go ahead and plug that into your calculator, see what you get. But what we'll find is that we get the same y value, +1.8. When we plug in +4, we see that we get the same output that we got when we plugged in -4 of 4/3. And recalling from our previous units, what do we call a graph that has this characteristic where when you plug in both a positive and a negative x value, you get the same y value? We can also see from the graph this physical characteristic of the symmetry. This graph is symmetric about the y-axis, so this function is actually even. A nice review of those terms that we learned in, I think, Unit 2. Okay, always good to go back and review that stuff. It's going to come back into play. We can see it here and then also for our final exam. So this is our graph of g of x. And let's look at another one. H of x equals 2x over x squared minus 1. Again, first thing is always find your domain. In other words, state your restrictions. So I'm going to factor the denominator. This, again, is a difference of two squares. So we get x plus 1, x minus 1. Our numerator doesn't factor, so we don't need to do anything with that. And we can see that x cannot equal plus or minus 1. That's our domain. Now we think about simplifying this function. Since there are no like factors in the numerator and the denominator, this is already in lowest terms. So our vertical asymptotes end up being the same thing as our restrictions. Now for a horizontal asymptote, since my function is bottom heavy, my horizontal asymptote is at y equals 0. To find our x-intercepts, remember we generalized in the previous example that finding our x-intercepts is just finding the zeros of your numerator. So to find our x-intercepts, that's where 2x equals 0 or x equals 0. So our x-intercept is 0, 0. And once again, since this is at the origin, this is also our y-intercept. All right, so let's go ahead and plot what we have now, and then we'll start looking at plotting additional points, making our table of values to graph our branches. Again, starting with our asymptotes, we have two asymptotes at -1 and +1. And we have a horizontal asymptote at y equals 0, which is the x-axis. Now I'm going to plot my other points in red just to show you so you can see a little bit better. But now when I go to plot my x and my y-intercept, look what happens. It's right there on that horizontal asymptote. So that's what I was saying before. You're probably going to identify where the graph crosses your horizontal asymptote at the very beginning of the problem. Very rarely does it occur at a point that's different than your x-intercept or your y-intercept. So we've already seen where this graph crosses the horizontal asymptote. And we can ask ourselves if it's ever going to cross the horizontal asymptote again. Well, the horizontal asymptote is my x-axis. If it were to cross it again, wouldn't we need another x-intercept? Yeah, we would. So since we only have one x-intercept, we know for a fact that this graph will never cross your horizontal asymptote again. So let's start making our table of values to get 2 points on each branch. Again, since we have two vertical asymptotes, we end up with 3 branches. One on the left, one in the middle here, and then one on the right. So graphing my left branch, I'm going to plug in x equals -2 and -3. When we plug in x equals -2, we get -4/3. And x equals -3 is -3/4. Now I'm coming up with these values, I've already got them, but make sure that you guys are taking the time to pause, make sure you can plug the x values into your function and simplify those fractions so that you have a point to graph. So at -2, we're at -4/3, it's going to be down here. And at -3, we're at -3/4 there. And we can use our asymptotes in those 2 points to sketch out that left branch. Now we'll plot another point on the middle. So we've already plotted 0, and if you look, there's no whole numbers or integers left to plug in. So we're going to have to go to fractions. So we'll plug in x equals 1/2 first. When I plug in x equals 1/2, we get negative 4/3. So graphing that point at 1/2, we're at negative 4/3, which is about down there. And based on the 2 points that I have, I'm still unclear about the shape of this middle branch. Is it going to be parabolic like we saw in the last example, or is it going to be more of a cubic graph in the middle? So if you're unsure, just plot another point. So instead of plotting positive 1/2 and 0, let's also add negative 1/2. What do we get when we plug in x equals negative 1/2? We get positive 4/3. So now that we've got negative 1/2, positive 4/3, now we can see the trend in that middle branch. It's going to be more like a cubic function than the parabolic function that we had before. So we're always approaching those asymptotes, making sure we go through those points that we've graphed. And now for our right branch, we'll plug in x equals 2 and x equals 3. And again, look at what happened in the middle here, in this middle branch. When we plugged in positive 1/2, we got negative 4/3. Then we plugged in the negative, we got the positive 4/3. So maybe that's a relationship between our input and our output that we'll see here in a second. Go ahead and plug in x equals 2. When you plug in x equals 2, we get positive 4/3. And what about x equals positive 3? If I'm basing off of what I've already seen, I'm going to guess that when I plug in x equals 3, we get positive 3/4. You always want to double check that, okay? But it is in fact true. When we plug in 2, we get positive 4/3. And 3, we get positive 3/4. And this relationship between our input and our outputs would indicate that this function is an odd function, which means that it's symmetric about that origin. Okay, let's try one more. We've actually seen this function, f of x equals 2 minus x over x squared plus 4x plus 4. Or no, I'm sorry, that's not right. We haven't seen this function. The next one we've seen before. To find our domain, we want to factor the denominator. This looks like x plus 2 times x plus 2. We needed factors of positive 4 that sum to positive 4, so 2 and 2. And then we've got 2 minus x in the numerator. From here, we can see that x cannot equal negative 2, and nothing's going to cancel out either. Be very careful. 2 minus x is not the same as x plus 2 at all, so just make sure that you're paying close attention. So because we can't simplify, we can go ahead and state our vertical asymptote, which is x equals negative 2. What about our horizontal asymptote? Again, if I look at my numerator and my denominator, the degree of my numerator is 1. Even though the x isn't in the front, that's still my lead term, and my degree is 1 over 2, so it's bottom heavy. So our horizontal asymptote is at y equals 0. To find our x-intercept, we set our numerator equal to 0. So adding x to both sides, we get x equals 2. So when x equals 2, our y value is 0. There's 1 point. And now, since it's not my origin, we can actually go about finding our y-intercept. And our y-intercept is found by plugging in 0 for x. So we have 2 minus 0 over I'm going to go ahead and, well, you can use, again, either form, the factored or not. 0 plus 2 times 0 plus 2, which simplifies to 2 over 4, or 1/2. So that's the ordered pair 0, 1/2. Let's go ahead and graph what we've got. We've got one vertical asymptote at -2. One horizontal asymptote at y equals 0. Now we've got an x-intercept at 2, 0. So again, there we're seeing where my graph is crossing the horizontal asymptote. And our y-intercept is at 0, 1/2. So right about there. Now I only need 2 points on each branch. So if we look, because I only have one vertical asymptote, I'm going to have 2 branches, one on the left and one on the right. And I already have 2 points for that right branch. So this will be enough to graph this. But I want to show you guys one thing. What's going to happen with this graph? As I come down from that vertical asymptote, I'm going to hit that x-intercept. And I'm actually going to go through my x-axis. But here we want to reinforce what a horizontal asymptote does. A horizontal asymptote is describing your end behavior. So this tail, as I get closer to positive infinity, actually needs to approach this horizontal asymptote. So I'm exaggerating here the turn that's going to occur so that, again, my tail ends up approaching that dashed line for my horizontal asymptote. To plot my left branch, we're going to plug in -3 and -4. And this one I don't have worked out, so I'll have to do this by hand. When I plug in x equals -3, we get 2 minus -3 over -3 plus 2 squared. That's 5 over 1, or 5. And same thing for -4. We've got 2 minus -4. Can you guys see this? I know I'm at the bottom of this page here. Over -4 plus 2 squared. 2 minus -4 is 6. -4 plus 2 is -2. Squared is 4. So this is going to be 3 over 2, which is 1.5. And now we have those 2 points, and we can use our asymptotes to shape that branch. If you have any questions about how to graph these using the online software, please make sure you just ask during class. I usually spend some time going over it, but if I don't get a chance to it or if I forget, just make sure that you ask if you're still unclear. All right, so let's look at one last one. And this was a function that we saw previously. G of x equals x squared minus 64 divided by x squared minus 5x minus 24. Again, starting with finding the domain, we're going to factor the denominator. Factors of -24 that sum to -5 are going to be -8 and +3. So right away, I can see that my restrictions are at 8 and -3. X cannot equal 8, x cannot equal -3. But I also know that before I find my vertical asymptotes, I need to simplify this function. So I want to go ahead and factor the numerator at the same time. My numerator is a difference of 2 squared, so that's x plus 8 times x minus 8. And there's that like factor of x minus 8 that we saw. So our function g of x can be simplified as x plus 8 divided by x plus 3. And now that it's simplified, we see that we have only one vertical asymptote at x equals -3, which means what's going to happen here at x equals 8? That means that at x equals 8, we are going to have a hole. So back to our work over here, we have our vertical asymptote. Our horizontal asymptote is going to be at y equals, again, the lead ratio of our lead coefficients is 1/1 since our degrees were equal. Our x-intercepts are where the numerator equals 0. So where does x plus 8 equal 0? That's at x equals -8. So we have that point -8, 0. And to find your y-intercepts, you're plugging in 0 for x. So I'm actually going to use the non-factored version, or it actually doesn't matter. We can use 0 plus 8 over 0 plus 3. Whichever form seems easiest for you, you can use, which is 8 over 3. So now we can start plotting some stuff. Starting with our asymptotes, we have one vertical asymptote at -3, one horizontal asymptote at 1, our x-intercept is at -8, 0. And our y-intercept is at 8 over 3, which is almost 3, not quite. So 2 2/3, I think. Now we know we're going to have a hole at 8, and we'll talk about that in just a second. But we can see here that we are going to have two branches, one on the left and one on the right. So we can start making a table of values for our second point for the left branch and our second point for the right branch. Since I already have one on each side, I only need one other point. So for the left branch, let's plug in x equals -4. When I plug in -4, I'm going to use this simplified version. It'll give me the same result. I have -4 plus 8 is 4 over -4 plus 3 is -1, so -4. Then for my right branch, I will also plug in, let's plug in 2. I just chose that so it was a little bit more spread out from this point, and I'm also looking at this is going to probably simplify pretty nicely when I plug in 2. It doesn't make any difference what points you pick, just, if you think about it a little bit more, you might make your arithmetic a little bit easier. And it might look a little bit better in terms of your graph. So when I plug in 2, we've got 10 over 5, which is 2. So we've got the point 2, here. Now this left branch is going to look like this, going through my 2 points, approaching my asymptotes. But my right branch, I need to be very careful. We still need to think about that hole. So how do I graph my hole? My hole is in my actual curve, isn't it? So if I were to just think about this line like this, what I need to figure out is where is the hole at x equals 8? To find that, plug in x equals 8 to your simplified version. So we get g of 8 equals 16 over 8 plus 3 is 11, which is 1 point something. I don't know what it is. But I can see that what's going to end up happening is I'm actually going to have an open circle right ooh, yikes. I need to go back to my pencil. I'm going to have an open circle right around here at 8, 1 point something, whatever it is. So that's how we graph our holes when they occur. So we've seen a lot of different examples of graphing rational functions. Notice we didn't actually see an example where we graphed an oblique function. That's not something that I'm going to assess you guys on. However, you still need to be able to identify and find oblique asymptotes. Even though you won't be graphing with them, you still need to know how to find them. All right, so let's look at one more example where we're going to start modeling a rational function. Again, modeling a rational function means come up with an equation that uses the characteristics that are given. So we want to write a model for a rational function that has vertical asymptotes at -3 and 1, horizontal asymptotes at y equals 3, an x-intercept at -1, 0, and that's all it's given, but I have indicated that there are multiple solutions possible. So let's think about what's given. We've got some vertical asymptotes. Now, if you look back to your previous examples, where did we find our vertical asymptotes? They were the zeros of your denominator. So we know that our function f of x is going to have a factor of x plus 3 in the denominator and x minus 1 in the denominator, so that we end up with those two vertical asymptotes. What about your x-intercepts? Those we figured out were the zeros of your numerator. So I know that I'm going to end up with a factor of x plus 1 in my numerator, since my x-intercept was -1. And now we're also given our horizontal asymptotes. Now our horizontal asymptote is going to tell us about the degrees. In this example, since our horizontal asymptote was at a number different than 0, that means that my degrees were equal. If we had had a horizontal asymptote at y equals 0, that would have told me that the function was bottom heavy. If we had been given an oblique asymptote or none of them, no horizontal or no oblique, then that just means that the degree in your numerator is more than 1 greater than the degree of your denominator. Since I know that the degrees are equal, let's look at what we've got here. Right now I've got x plus 1 in the numerator, a multiplicity of 1. X plus 3 times x minus 1, each of those have a multiplicity of 1, so I've got a degree of 1 over a degree of 2. I need to make the degrees the same. The only way I can do that is by squaring this. I don't have another x-intercept to put another factor there, so I square this factor. Now, also because the degrees are equal, this is giving me the ratio of my lead coefficients. So I know that this number divided by this number needs to be 3, so I can account for that by just throwing a 3 out front. Now, again, I've mentioned that this is only one possible solution out of many. I could change the degrees of all of these zeros, just as long as the degree in the top is equal to the degree in your denominator, then you're going to have a function that satisfies these given characteristics. Now, you'll see in your homework some examples of writing a function given a graph as well. So the same thing, we're just pulling the information from the graph instead of out of a paragraph. To recap, vertical asymptotes are going to be your zeros of the denominator. Your x-intercepts are going to be the zeros of your numerator. And then if they're given information about a horizontal asymptote, that tells us the relationship between the degrees of the top and the bottom of that rational function. Make sure, guys, when we're looking at rational functions, we always state the domain first. The domain is the restrictions in the bottom before you simplify anything. That always has to come first because that's going to help us identify if we have any holes in our function. Once we've stated our restrictions, then we can go into finding our vertical asymptotes and our horizontal or oblique asymptotes. For the test, we're going to require that you guys graph 2 points on every single branch. So make sure that you guys make your table of values, and plot 2 points for every single branch. And you're going to determine the number of branches just by looking at your vertical asymptotes. If you have one vertical asymptote, you're going to have 2 pieces. If you've got 2 vertical asymptotes, then you're going to have 3 different branches, so on and so forth. So good luck with that, and we'll see you guys next time for the beginning of Unit 5 for exponential and logarithmic functions.